All right, let's start talking about some of the characteristics of something called a periodic function. So basically, it has y values that repeat after a while. So you can see in this first picture here, they've got kind of a zigzag pattern. You know, it starts down, goes up, goes down, goes up, goes down, and in the beginning, we're really talking about periodic functions who go up and down to the same heights. Uh, so basically what you're looking for is, I'll highlight it in red here. You pick a place to start, usually somewhere around whatever the input variable is. In this case, it's theta, right? Usually you start around the origin. Don't have to, but it's good to start there if you can. And you can see I have them all the way up here at 1. And then I go down to -1, and I show back up to +1 again. That is called a cycle. And the reason why that is a cycle is if you were to grab that shape and slide it on over, it'd fill in the next part exactly. And you could keep doing that. You see how it just keeps going over the top? It's like that's the part that's repeated. That's the idea. You're basically looking for the part that's repeated. As long as you see that shape is getting repeated over and over again, you found yourself the cycle. Now, what's important about identifying the cycle is there's some domain. Here we start at 0, and we see we end at 360, where the function describes all the different points in that cycle, which means in the next cycle, all of those y values have already been, we already know what they're all going to be, and they all correlate to some other number in the period where it's kind of repeating. And that's the idea behind the period is, what is the domain of what's repeating? So from 0 to 360, we have a cycle. From 360 to 720, we have the same exact cycle. From 720 to, we gotta add another 360, 1080 would be another cycle. So that's the idea. It's where is it repeating? Where is it repeating? The cycle is the whole graph. The period is just the input of the function. Looking at the table here, you can see we go from 1 to -1 to back to +1 again. And that happens between 0 and 360 degrees. And we go from 1 to -1 to 1 again, from 360 to 720 degrees. So the period on the left, on the outputs, you're looking for the pattern that shows you that it's repeating. Okay. And so when we describe the period, it's always described by the input. Example 2. Identify the period. So we're taking a look at this shape here. Determine the period of the function. The first thing I notice is that the theta this time is in radians. And that's just fine. Radians are a different way to measure angles. So I just know I'm not going to be describing it in degrees. I'm going to be describing the period in radians because that is how the input is described to me. Now, if it helps, get a little tracing paper, you can trace it out. For me, I can just do it straight on the screen, but I can kind of draw out. It comes down, goes flat, and goes right back up again. And if I take a look at that piece, I could take it and I could drag it over, and look at that. It gets repeated again. So that would be my cycle. That little looks like a cup, doesn't it? Doesn't that shape look like a cup? Yeah, looks like a cup. So that cup is my cycle. I start at 0 and I end at pi. So the period is pi radians if you really want. You could just write pi. We assume that if you're writing multiples of pi down, it's in radians. There you go. That's all there is to it. You just got to figure out where it repeats and then figure out what the domain is for that region that it repeats.